So now let's talk about more complicated models. All the models we've talked about so far, we've had to make very great simplifications and approximations to make them tractable. We've had to assume that the past is just like today, or that you can extrapolate, or that a very simple model works. And until recently that was all you could do, but now with the advent of powerful computers it's possible to make your models much more complicated. So let's start off with talking about some examples. Let's talk about disease models. We've just talked about the simple SIR model, which is where you assume that everyone behaves the same. That of course is clearly a gross oversimplification. A real model has to allow for the differences of people, that not all people behave the same, have the same ages, the same susceptibilities, the same social networks, and should also allow for changes in behaviour. And these models are what are actually used to control pandemics. So this is the Australian Pandemic Committee being briefed about one of these models. So the basic idea for these more advanced models is you might simulate a large number of people in your computer. It's like an agent-based model. So you might simulate, say, 10,000 people. So for each person you would randomly give it an age, a location, the size of its social network, how healthy, male, female, whatever it might be that's relevant. And then you might put a few random bits of infection in there and see what happens. So if you randomly infect someone with a big social network, let's say they're at the cafe like down here, they might infect more people. And some of those might have a very small social networks and not spread anybody else. Those who are old would have a high chance of dying from something like COVID that mostly affects the elderly, whereas young people don't die but might go to school and pass it on. You can use census data to build the entire thing, so you'd be a realistic snapshot of, for example, how many kids are at school. And these give predictions like this. This was during the Victorian second wave outbreaks. You had the first wave of cases in Victoria. This is the number of COVID cases. Then it was rising fast. And then here are projections with a fairly large uncertainty. We'll talk about them later. You get from multiple runs of the code, so depending exactly what assumptions you make about what fraction of people who have COVID have actually been tested, and whether these people are, maybe there are lots of kids who are not being infectious and so on. And these models can be extremely useful because they can address issues like, if we close the schools, how much difference will that make? If we lock down but let essential workers keep working, how much difference will that make? How much difference will a vaccine with 50% efficiency make? It can actually give you the sort of answers to questions that policymakers really want. These sort of agent-based models are also very important in economics. Instead of the simple like supply and demand models we talked about in the past, an agent-based model, once again, you might put several thousand random people and give them all incomes and jobs and ages drawn from census data, and then you can see what happens. So each person might be interested in making themselves richer, and they'll have particular skills, and then you can let them all interact with each other in the simulation, and like some giant version of the computer game The Sims, and see what actually happens. And NatCen, the National Centre for Social and Economic Modelling here in Canberra, does a lot of this, and they can answer questions like, here they've got a simulation of a particular change to disability support and which parts of the country it will cause highest and lowest changes in incomes. So they've used census data to find out how many disabled people are in different parts of the country and what their incomes are and who'd be eligible. So you can again say, for a particular policy, who's it going to affect, where are they, how might that flow through to the local economies, and so on. So these more complicated models, which use the power of modern computers, where you actually simulate individual people or simulate large numbers of people, can often get you answers you couldn't get from a big, simple macroeconomic model. And of course we have weather and climate modelling, where you divide the atmosphere into cubes, and then for each cube of the atmosphere you work out the pressure and density of the air on all sides of it and how it's all flowing. And as time has gone on, the computers have got faster, so you've been able to divide the world into smaller and smaller cubes, make it more and more realistic. And you can see this in the accuracy of weather forecasts. So here, going from 1981 to 2018 is a measure of how accurately the forecasts predict what says the 500 hectopascal geopotential height, which is basically a measure of air pressure. And you can see that like a 10-day forecast now is as accurate as a 7-day forecast 20, 30 years ago, and so on. As the 7-day forecast is better than a 5-day forecast in 1990. So the forecasts are steadily getting better because they're getting better at building the models, and they have faster supercomputers to subdivide all the atmosphere up into its cubes. So that's another form of modelling, computer modelling, which is where you put the details in by using a computer, which often means dividing it up into, for example, individual people or individual blocks of the atmosphere or something like that. These are very common, for example, computational fluid dynamics models in simulating aircraft and so on. So it's a thing that physicists and engineers are very used to. There is one new technique of modelling which has come about just in the last few years, which is to use neural networks, artificial intelligence, the deep learning models. These models, you train them on large amounts of data and then ask it to predict things in the future. These are what are behind, for example, ChatGPT and other models like that that predict the next word you're going to say. But if you've got a lot of data, you can just use them to predict the future. So, for example, they are currently being used for weather forecasts. What you do is you feed in all the weather data and then ask it to predict what's the weather going to be like 1, 2, 3, 4 days in the future, or whatever. And then if it gets it wrong, you tweak the model until it gets better and better, and you train it, because you've got lots of data. You've got the weather observations for all over the world for the last many decades. And these are now becoming pretty good at predicting the future. They don't actually model the physics of air density and flows and so on, but they're actually getting fairly good just from sheer practice. This is kind of like going back to the find an example in the past, where you just practice. It's a black box model. You don't know what's going on inside it, but you just train out on all the data you've got in the past, and then it predicts the future. And these things can run on much smaller computers. You could run one of these things once it's been trained on your laptop, which you certainly can't do for a supercomputer global climate model. So that's the latest technique. Of course, given it's been trained on historical data, it's never going to tell you unexpected things in the future, like global warming. But for day-to-day prediction of things like weather and stock market movements, it might do quite a good job.